Very good. And the last speaker of the session is Marinka Zitnik from Stanford, talking about modeling polypharmacy with graph convolutional networks.
Hello, everyone. Today I will talk about predicting side effects of drug combinations with graph convolutional networks. So many patients take multiple drugs to treat a disease. And the use of multiple drugs is known as polypharmacy and is especially common in treatment practice for complex and coexisting conditions. For example, 25% of people ages 65 to 69 take at least 5 prescriptions of drugs to treat chronic conditions. And it's not uncommon to encounter patients that take more than 20 drugs to treat complex diseases such as heart disease, insomnia, depression, and other disorders. While the use of multiple drugs may be really a good practice for treatment of many diseases, a major consequence of drug combinations for a patient is a much higher risk of adverse side effects. So these side effects can lead to new problems which trigger additional prescriptions, a process known as a prescribing cascade. So the side effects can emerge because of drug-drug interactions, meaning that activity of one drug changes unfavorably when taken together with another drug. So consider an example shown here on the slide where we have two drugs, red and blue drug. So the idea is that when a patient takes either red or blue drug alone, there are no side effects. However, only when the patient takes both red and blue drugs together, the side effect occurs. So such side effects are extremely difficult to identify manually, primarily because there are combinatorically many ways in which a given combination of drug can clinically manifest, also because each combination of drugs is only valid in a certain small subset of patients. So furthermore, polypharmacy is also recognized as an increasingly important and serious healthcare problem that affects a large fraction of population. So because of that, it's important to screen drug combinations for unwanted side effects, and because this has significant implications for patient mortality. So traditionally, safe drug combinations have been identified by experimentally screening all possible combinations from a predefined set of drugs. However, these experimental screens are very challenging, both in time and costs, because, for example, given n drugs, in principle, we would need to check and choose 2 combinations just to examine drug pairs. And there are many, many more higher order combinations. So to address this combinatory explosion, there were many computational methods developed, and roughly we could categorize them into classification-based methods versus similarity-based methods that either take known drug-drug interaction, drug-drug pairs as positive examples and random drug pairs as negative examples and form a classification task, or they score similarity between drugs based on various types of evidence. However, all these methods don't really predict side effects of drug pairs. What they predict is probability that the pair of drug will interact, meaning that we will see some effect that is beyond additive effect. So they do not really predict side effect, which is what we would like to do here. So we think that it's much more important and much more useful in terms of generating actionable insights to be able to answer whether a pair of drug will actually interact with a particular type of side effect. And even though identification of precise side effects is critical for improved patient care, as we have seen, it remains a challenging task that has not yet been studied through predictive modeling, which we would like to address here. So why is this a difficult problem? There are a number of challenges that need to be solved if we want to accurately predict side effects associated with drug pairs. First, there are thousands of different types of side effects that a patient can get. And each side effect actually occurs in a small subset of patients. Furthermore, side effects are interdependent in each other. For example, if we take a side effect that affects a particular organ, all side effects that affect a particular organ system, such as cardiovascular diseases, we could assume that they are some underlying common biological factors. Furthermore, for many drug pairs, we don't have any information about side effects that they might cause, and this can happen because a drug pair is not yet used in patients, or because it's not yet used in a sufficiently large number of patients so that we could reliably measure side effects. And finally, there are a number of different data sets that span molecular, pharmacological, and phenotypic words that could be potentially useful for this task, and it's not entirely necessarily clear how to combine and merge them for prediction. So our approach here is to develop in silico screening method of drug combinations, where we use molecular drug and patient data to predict side effects of drug pairs. So our task is, given a drug pair CD, we want to predict side effects of that drug pair. What is important here is that what we are interested in predicting are side effects that cannot be attributed to either drug alone. So we're not interested in predicting side effects of individual drug, but rather side effects that are specific to drug combinations. So we use a language of graphs to mathematically represent our domain. In particular, to describe which drug pairs lead to which side effects, we represent each side effect with a different edge type. So here, for example, drugs C and D lead to bradycardia side effect. And it's important, again, to note here that this means that if C and D are taken together, then there is a particular probability or population risk ratio associated with the two drug pair that a patient will develop bradycardia side effect. Of course, drugs C and D may lead to many other side effects with different drugs. For example, it can lead to 3 different types of side effects with drug C, which will be shown here as multiple edges between C and S node. Each edge will be of different type. And we have many drugs in the system, not only C, D, and S. Furthermore, we have information about what are protein targets of individual drugs, which is shown here in these orange circles, and the interactions between protein targets represented by protein interaction network. So altogether, we consider this 2-layer multimodal network of where nodes are of 2 types, drugs and protein. And in our case, the drug-drug interaction network, which encodes side effect types, will encode around 1,000 different side effect types, meaning that really what we have here is a highly multi-relational graph on which we want to make prediction. So using this mathematical formulation, our goal is we can reformulate our goal essentially by saying, given a partially observed graph where certain edges are missing, and these represent correspond side effects of our drug pairs, we want to predict labeled edges between drug nodes. So a query of the system is, given a drug pair CD, how likely it is that an edge CD, which is of type R2, would exist between those 2 drugs. So the approach that we are using is called graph neural network. Graph neural network is a really popular class of neural networks that are developed for graphs data. And I will talk a bit more in the next few minutes what I mean by that. At the high level, the idea is that the input is a graph, not an image and not a sequence. And we apply a sequence of layers, which are spatial convolutions defined on graph, in order to learn the weights such that they are most useful for our prediction. So what are graph neural networks and how they are different from other types of neural networks? So there has been lots of discussions and lots of talks in the last few days where people have mentioned deep neural networks, in particular CNN models and recurrent neural networks. And in fact, modern deep learning toolboxes are primarily designed for grids or simple sequences. What do I mean by that? So you can imagine images as a simple grid where each pixel is a node, and that pixel has some neighbors going up, down, left, and right, and you might have multiple channels. Similarly, you can think of sequence being yet another graph, which is a simple linear chain. And if that is if you think of sequence like that, which is what most recurrent neural networks think of, you can define sliding windows, you can define Word-to-Vec skip-gram objective models, and various types of recurrent networks. However, real-world graph data or networks are far more complex, so they can have arbitrary size. It's not the case that every node has 4 neighbors, as would be the case in the image graph. They're much more complex, they have more topological structure. Furthermore, there is no fixed ordering or reference point. So what do I mean by that? You could simply, if you take a matrix representation of a graph, which is adjacency matrix, one could simply perturb or sort of exchange the few rows and columns. That would result in topologically exactly the same graph. However, as if used as input to a regular neural network, our prediction would be completely different. Furthermore, these neural networks are often dynamic, sort of the networks in the graphs that we are working with are often dynamic and have multimodal features. So it's not really clear how to use them as input to neural networks. So the idea of graph neural networks is that they generalize convolutions beyond simple lattices that we have when we deal with images or text data. So at the highest level, our approach, which is called Decagon, consists of two components. The first component is encoder component. What encoder component does, it takes that multimodal graph that we have seen, and it learns an embedding, a d-dimensional feature vector for every node in the network. In the second stage, which is the decoder stage, we use the learned embeddings, and we combine them in a way that's most useful for predicting side effects. So what do I mean by embedding nodes? What I mean by embedding nodes is that intuitively what we want to do is map nodes to some d-dimensional embedding space such that similar nodes in the graph are embedded close together. And there are various notions how to define the similarity of nodes in the graph. Intuitively, what we want to learn is this mapping function f that will take a graph and it will learn some d-dimensional embeddings. The key idea of graph neural network is that we will generate those node embeddings based on network neighborhoods. In particular, we will model each edge type separately. So consider here, for example, a toy example, or sort of to illustrate this point, let's consider this example that is shown on the left, and let's focus on the dark green node in the center. So what you can see that this dark green node has 4 neighbors, 2 of which are of type R2 and 2 of which are of type R3. So what we will do here is actually, using neural network, we will learn how to propagate vector-valued messages, which are information across the network following the edge type semantics. So in the R2 channel, which is R2 edge type, this dark green node will receive information from 2 other neighbors that are through which it is connected through R2 edge type. Similarly, for R3, it will receive information from 2 other neighbors that are related to this dark green node through R3 edge type. And then it will learn how to aggregate that information and how to use it as input to the next layer. So the way we can think of it intuitively is that network neighborhoods will define a computation graph. And every node in the network will define a computation graph. Think of it as a small neural network based on its neural neighborhood. So let's examine a neural layer architecture for one layer and for one node. For example, for this central drug node C. We can see that C has a bunch of neighbors. It is involved in 3 different types of edges, 2 side effect types, and it has 3 neighbors that are drugs, and it also has 4 drug targets. How this will look like, this means that we will have, because we have 3 edge types, we will have 3 different channels in our computation graph for that drug node. In each channel, we will learn how to get information from neighbors according to this channel, and then the information from the 3 channels will be aggregated and non-linearly transformed using an activation function such as ReLU, and that will be used as output of the current neural network layer. Finally, if we repeat this procedure k times, we get a final embedding that represents the embedding for the node. So this is really just an update for one node in the network. We have many different nodes, so we get lots of different computation graphs based on the neighborhood structure of the nodes. So you might wonder, well, how can we then learn if we have so many really small neural networks? So the idea is really to share parameters across neural networks in order to be able to train them effectively. So this is the encoder stage of the model. In the decoder stage of the model, as I said, we take the embeddings, these low-dimensional vectors, which are shown here in blue as blue vectors, and we learn them how to combine 2 embeddings of 2 drugs in a way that will be able to predict side effects. In particular, what we can do is using a tensor-based factorization decoder that allows us to predict probability of association between a drug pair and a particular side effect. So at the high level, Decagon has 2 components that, when taken together, form an end-to-end model that we can optimize for performance. So during training, we optimize model parameters using the loss function that encourages the model to assign higher probabilities to those drug pair, the side effect associations that are in the data, and lower probabilities to unknown drug or negative drug pair side effect associations. And the result is really a fully trainable model for multi-relational link prediction that starts with graph as input and was able to answer these queries. I know that I was not really able to go into details behind graph neural networks, but on the first day of the conference, which was on Friday, we had a tutorial for deep learning for network biology. And I really encourage you to check the materials, which are at snaps.stanford.edu/deepnetbio-ISMB. So in that tutorial, you will find theoretical derivations, motivations, as well as various graph neural network models that can be used for problems in biology, including biomedical applications. You will also find popular code bases in C++, Python, PyTorch, and TensorFlow, as well as network datasets, so you can start playing with the graph neural networks. For the rest of this talk, let me talk more about the experiments that we did. So for the experiments, we used first, to construct the heterogeneous graph, we use large molecular drug and patient data set. In particular, we considered protein-protein interactions that are physically documented in human, drug-target relationships, and side effects of drug pairs from a resource developed at Columbia University. So altogether, that resulted in a heterogeneous multimodal graph that we have seen before with around 1,000 types of edges. After constructing this graph, we formed a prediction task as following. So in the training phase, we fit a model on known side effects of drug pairs. In the testing phase, given a query drug pair, we predicted all types of side effects associated with that query drug pair. There are a number of different settings that we considered to prevent any circularity in the data. To show the results, let's look at this slide. So the performance here is measured in terms of two metrics, in particular area under ROC curve and average precision at 50, where we were looking at top 50 predictions and what is the accuracy for those. We compared Decagon, our model, which is shown in the red bar, with a few other alternatives. What we can learn from that is that it performs much better than tensor-based factorization models. The reason why this is the case, because we're using graph convolutional encoder. It performs much better than two-stage pipelines. Those are pipelines that you take a network, first extract features, take the feature vectors, train a downstream classifier, and this is because we have an end-to-end pipeline, end-to-end model. Just to conclude, well, we were also interested in doing de novo prediction. In particular, we predicted associations between all possible drug pairs and side effects, ranked them by the predicted probability score, and look at top 10 predictions that were not in the data, and see, well, can we find evidence for those? It turns out that for 5 out of those 10 predictions, we were able to find evidence, and there are other predictions that are currently explored at Stanford by Spark Translational Research Center. So to conclude, today I talked about Decagon, which is a graph neural network that can work and operate on heterogeneous graph. It has lots of flexibility and is super scalable. It can integrate side informations in terms of as node features on the nodes, which I didn't really go into in this presentation. This is the first method that can predict model drug combinations. It can be useful to predict drug combinations that are not yet used in patients. We have all the code and data for this project up at snap.stanford.edu/Decagon, and all the materials about deep learning for network biology tutorial on the other website. Thank you.
Very much. Are there questions? One over there.
Impressive work and presentation of the work as always. So your framework has two components, the embedding part and link prediction part. Which one contributes to superiority over the existing methods, and in particular, why not use Node2Vec or even better MetaPath2Vec, which is heterogeneous version of Node2Vec, as embedding part in your framework rather than using logistic regression on top of it?
Yes, so that's a great question. So we compared the performance of our model with the two-stage pipeline, where the idea was to first take the network, learn node-to-weak embeddings. We also did experiments with meta-pet-to-weak proposed by that KDD paper last year, and then using logistic regression on that. It turned out that what was really important here is that because we have 1,000 different side effect types, you can think of these as 1,000 different classes with strong interdependence between side effect types. It was important then to learn embeddings for all side effect types by distinguishing side effects, and then have one model that can map embeddings from this latent space to the final prediction probability space. So what we found that you asked if we have two components, what's the one that's more crucial? This graph convolutional embedding that can take into account relation types, so edge types, was more important for final prediction performance, which we can see by greater difference in performance between the red bar, which is Decagon, versus the blue and brown bar, which are these tensor-based factorization models.
Okay, I think so. I think my question is very similar, actually, to the other one. So my question is the same. Like, what would be if, like, you were to learn these embeddings first on the drugs, and you could do that in an unsupervised way, and you can use many more. Because here you can do it for drugs for which you know in your training set, but then you can just learn embeddings in an unsupervised way for the drugs, and then you just take those embeddings and kind of like concatenate them or something, and then feed them into a neural network with multitasking, which kind of uses this embedding to predict all these side effects. It's a multitask network, and like you said, the side effects are interacting, so they can benefit from being trained together. So how would that be different? And for learning the embeddings, why not just using a simple neural network as well?
Yes.
So how that would compare with your approach?
Yes. So that's a great question. I have a few answers to that. First is, we did compare our method against this two-stage pipeline where you take a network and use network embedding method. And this is the red bar versus the last green bar. So the last green bar represents node-to-weak plus logistic regression, which is the standard pipeline where you take the network, learn embeddings in an unsupervised way, and then you solve a bunch of smaller logistic regression, or you can do softmax regression, or you can use like a two-layer fully connected network on the embedding space. We observed that the performance from our model is much better than these baseline models. And furthermore, what this graph neural network can learn are dependencies between side effect types. Yeah.
Thank you. One last question over there.
Thank you. Great talk. A really fast question. So when you said, when you're embedding, you want similar patterns to be close to each other. So when you did, for this study, what is the similarity metric for doing that?
So the similarity metric for that is such that we do not need to explicitly define the metric. The idea is that in each layer of the neural network, every node will receive information from its direct neighbors. It will learn how to aggregate that information and then normalize it, and then non-linearly transform it. If you stack two layers of graph neural networks together, what you do, you learn how to aggregate information within two-hop neighborhood of your node. So more classical methods such as random node-to-weak or meta-path-to-weak models need to simulate a large number of random walks, and they use that to define neighborhoods. In graph neural networks, you don't need to do that because you will learn what's the contribution of every node in your k-hop neighborhood if you have k layers of neural network. And that's done as part of learning process.
Okay, thank you.
Thank you very much. Let's thank Marinka again. And have a good break, and please be back at 2 o'clock because we have the next keynote by Alexis Bettel, which will be great. Be here.